You have a projectile that's launched at 22 meters per second above the horizon here, above the horizontal. It's going to go up in the air, come back down. Delta y is equal to 0 for the whole problem. That's important because the equation we're going to use is only valid when it ends up back down at the same level it started. So it goes into the air at 22 meters per second and it lands 25 meters away. And then the question is, what are the two possible launch angles? So the equation we're going to use, we derived this in class, is this one. R equals V naught squared sine 2 theta naught, that's the launch angle, initial angle, all over G. Again, this is only valid when that's true. Never use it if that's not true. Let's solve for sine 2 theta and multiply both sides by G, divide by V naught squared. So that equals R times G all over V naught squared. And R is 25. G is 9.8. That's not negative. Don't put a negative sign in front of that. G itself does not have a negative sign. Then all over the launch speed of 22 squared. Well, when you do that, you come up with 0.5. 0.5. So the 0.5 is the sine of, I'm going to put a parentheses here, 2 theta naught. So that 2 times that angle. There are two values that have a positive sign. You have a positive sign, plus 0.5, in the first quadrant and the second quadrant of a graph. So when you do the arc sign of this, sine to the negative 1 of 0.5, you're going to get two answers. On your calculator, it's just going to give you one answer. It's going to give you 30 degrees. But that's the first quadrant. You also need to find the answer in the second quadrant, which would be 180 minus 30, which is 150 degrees. Again, these two are, what, supplementary, I think that's the term. Okay, 30 degrees in the first quadrant, and then 180 minus 30 is 150 in the second quadrant. Well, those aren't the answers. Well, if you're trying to shoot this thing to the right, 150 is to the left. That's because we're not done. You need to divide by 2. Okay, this is 2 theta. So what's theta? Well, 30 over 2 is 15 degrees. And 150 over 2 is 75 degrees. Those are the two launch angles that at this speed and at that range, either one of those will give a range of 25 meters. I think that's interesting. That's the only thing that's the same, though. Obviously, at 75 degrees, it's going to go higher. It's going to be in the air longer. At 15 degrees, it's not going to go as high. It's going to have a greater value of Vx. At 15 degrees, it's not going to go as high. All that stuff's different, but they're going to land at the same place. The other question I've seen that goes along with this is show that 45 degrees, when delta y is equal to 0, show that 45 degrees is the angle that maximizes the range for a projectile. Well, that comes from this equation right here. So if you're trying, well, you can't change the value of 9.8, right? That's 9.8. And if you're trying to water the flowers or something, you've got the hose cranked on as fast as it can go. You can't change that anymore. All you can do is change the angle that you hold the hose. So that's fixed. That's fixed. As you change the angle, you're going to change the range. So how do you maximize that? Well, you maximize it by mathematically, what's the largest value you can ever get out of this thing? Well, the largest value you can ever get out of that is the value of 1. Well, the sine of what angle gives you 1? Well, the sine of 90 degrees gives you 1. So 2 times what equals 90? 45. So 2 times 45 degrees will give you 90. The sine of 90 is 1. That's the largest value you can get there. That's how you maximize the range of a projectile in which delta y equals 0. I have seen that on an AP test before.